So today we're going to be talking about section 4.3, which is on dividing polynomials. So one of the easiest ways to divide polynomials anytime we're dividing is to use long division. So we have to go back and review what long division is. So if you think back when we would divide like 17 by 3, right? We would say, okay, well, how many times does 3 go into 17? The correct answer is 5. And then 3 times 5, so 5 times 3 is 15, and we would subtract, and there'd be a remainder of 2, which means it'd be 5 and 2/3, okay? So that is how we can do division of polynomials too, kind of the same idea. So you figure out what goes into your section and go on from there, okay? So what we're going to be doing is we are going to be looking at polynomials right here, okay? And so if we're going to be dividing f of x and g of x, you're going to get some new polynomial that will be of less degree, and there can possibly be a remainder. And so that's what this is kind of saying right here. If there's a remainder polynomial, we would take that divided by what our original amount was, just like in that problem we did. Our remainder was 2, and so we left it as 2/3 because we were dividing by 3. So remainder of 2 over 3. We can do the exact same thing with polynomials, okay? So let's take a look at a problem, including that we can use long division to simplify, okay? All right, so we are going to look at the problem. Okay, here's our problem right here. We're going to look at 2x to the third plus 3x squared plus 4x plus 4 divided by x plus 1. Okay, so the first thing we're going to do is we're going to look and we're going to say, okay, well, I'm looking at this value right here, and I'm going to say how many times does x go into 2x to the third, okay? Well, x goes into 2x to the third 2x squared times, okay? And to keep things nice, I'm actually just going to put it over the other x squared, okay? And the reason I picked that is because now 2x squared times x is 2x to the third, and then 2x squared times plus 1 would be plus 2x squared. And then we subtract down, right? So this will go away. There'll be nothing left here. 3x squared minus 2x squared is just x squared. And then I drop down plus 4. Okay? All right? Or excuse me, 4x. And so now I say, well, how many times does x go into x squared? That's 1x times, right? So x times x is x squared. X times plus 1 is plus 1x. I subtract down, and I get 3x. And so I say, well, how many times does, all right, I actually have to drop this down to plus 4. So how many times does x go into 3x? Well, it goes in 3 times, right? And so I move it up just a little bit, okay? And so then that would be 3x, and then plus 1 would be 3, and I subtract, and I have a remainder of 1. So I come back up here, and this is where the remainder part is important. I'm going to do plus 1 over x plus 1 because 1 is my remainder. That's what I had left over. Okay, that is my remainder. So my correct answer would be this, 2x squared plus x plus 3 plus 1 over x plus 1. Okay? All right, and so we can continue on doing long division for any one of these problems. Now, long division takes more time, and it's more writing and things like that. So we created a new thing called synthetic division, where essentially you're going to be doing the same thing, except for you'll be using only the coefficients and the powers of x, as long as they're in descending order, okay? So let's look at one. Same sort of problem, right? And it's going to look like this, okay? So in fact, let's use the exact same problem, right? So again, here's our problem, 2x squared to the third plus 3x squared plus 4x plus 4. And we know, and that's all divided by x plus 1. So we know that this is going to we'll know what our answer is, and we know that it has a remainder, okay? So let's just verify this one with synthetic division. So what we do, first off, is we create a box, okay? Sometimes we call this the box method, and that's coming from this. Now, remember, when we're doing synthetic division, okay, we always want to be of the term, we want to think of this as x minus r. So r is our root, and so we have x plus 1. So r in this case has to be -1 because x minus a -1 is the same as x plus 1. Okay, so that's important. Okay, so let's put a little star by that because that's important to remember. All right, so now what we're going to do is we're going to look at all the coefficients, okay, in descending order. So x to the third, x squared, x, and then our constant is going to be right there. So we're going to write our coefficients. So it'll be 2, 3, 4, and 4, okay? And then we draw a line underneath it. Now for the first one, just like we did before, right, it's pretty easy. We drop this number down. So it'd be 2, okay? Then -1 times 2 is -2, and we add down. So it's going to get 1. Do the same. -1 times 1 is -1. We get 3. Okay? -1 times 3 is -3, and we have a remainder of 1. So this is going to be our remainder. Okay? So our solution now, okay, so when we started with x to the third, right? And when we drop down by a power. So now our solution is going to be 2x squared plus x, or 1x, plus 3 plus our 1 over x plus 1 as our remainder. And you'll notice this is the same solution that we got for this one, okay? Or as example 1. Now, the next thing we can talk about is the remainder theorem. Now, the remainder theorem is interesting in the fact that it's using synthetic substitution or synthetic division. Sometimes we call it synthetic substitution. But what it is it's basically if you were to put a value in for x if you want to put the value into x, you basically can do synthetic substitution, and whatever you have left over is actually what it is if you would have put it in. Okay, so our remainder theorem basically says this. Here's word for word what it says. If the polynomial f of x is divided by c, x minus c, then the remainder is f of c. Okay, so basically it is if you're going to, so like in that last example, okay, so if we're dividing by x plus 1, if I put -1 into the function, I would have got out 1 in the end, which is interesting, right? We could try it and it works. Okay, so let's actually look at a problem and we're going to figure out what it is. Okay, so let's look right here. Okay, so I am going to I have some function h of x, okay? And I want to know if h of 6 equals -11. What do I know about this? Okay, well, what do I know? Well, what I know for sure is that when h of x is divided by x minus 6, it equals 11. I know for sure that's what, or excuse me, -11. I know for sure that's what it is. Okay, I know for sure that's the case. Now I don't know anything more than that, and that's not important at this point. But this is what I know to be true. Okay, if I take the function f of x like that, it's going to have a remainder, I guess, of -11. I shouldn't say it's equal to it. Will be the remainder. Okay. All right, so that's important to know. Let's see. That's pretty much it. Okay. All right, the last thing we can talk about in section or in this section is the factor theorem, and it basically says this. Okay, so here's word for word what it is. It says the binomial. Remember, binomial means two numbers. The binomial x minus k is a factor of f of x if and only if. Okay, so here's the symbol for if and only if. Goes arrow going both ways. If and only if f of k equals 0. So basically it says this: if whatever our factor is that we're trying to, or our root or whatever, our k, that we're trying to figure out if this is a factor, we're going to plug that into f of x using synthetic substitution. It's a fast way to do it. And we can find out if it's equal to 0, if it doesn't have a remainder, then it is for sure a factor. But if it does have a remainder, then it's not a factor. Okay, that's important to know because that's going to help us later on when we start looking for roots of bigger polynomials. All right, so let's look at a problem. We are going to look at let's look at this problem right here. Okay, I have 2x to the fourth minus 3x squared minus 12x, okay, and then minus 7. And I want to divide that by and see if this is a factor if x minus 2 is a factor, okay? I want to see if x minus 2 is a factor of this polynomial, okay? So what that means is I am actually going to I'm going to create my synthetic substitution problem, right? I'm going to create it. And so my box, I'm going to put in 2 because it's always, remember, x minus r. So r in this case is 2. I'm going to write my coefficients. Now, there is something that's rather important. Notice that this is power 4 and then this is power 2. Where's power 3? Well, power 3 actually is there, but its coefficient is 0. So we need to make sure we make note of that. So it's going to be 2 because that's x to the fourth, 0 because that's x to the third, negative 3 because that's x squared, negative 12 because that's x, and negative 7 because that's our constant, okay? Now, the first thing we always do is we drop down the 2, okay? It drops down. Now the powers drop down, right? 2 times 2 is 4. When we add down, we get 4. 2 times 4 is 8. Okay, so we add down, we get 5. 2 times 5 is 10. So I get negative 2. 2 times, that would be negative 4. Or excuse me. Yep, negative 4. And then I get negative 11. So I notice right here, does this actually have a remainder of 0? The answer is no. So this is not a factor. X minus 2 is not a factor of my original polynomial. Okay. Okay, so let's look at one where there actually is a factor. Okay, let's take a look at that. All right, so we will have, okay, so I'm kind of giving you an example here. So x to the third plus 5x squared minus 9x minus 45, okay, all divided by x plus 5. Okay, so we're going to see if this actually is a factor. Okay, here's the hint: it is. Okay, but how do we prove that, right? So my box is going to be negative 5 because we always remember we want x minus r. So our root in this case would be negative 5. Our coefficients are 1, 5, negative 9, and negative 45, checking to make sure we didn't miss anything, right? So x to the third, x squared, x, and then constant. Good. I drop down 1. That'd be negative 5. All of a sudden I have a 0 here. 5 times 0 would be 0, obviously. Then we get negative 9. That would be 45. And I have a remainder of 0. So now we know for sure that this is a factor, right? And then from here, we can actually figure out what our next factors are by having our new solution, right? So that would be x squared, and then 0x, and then minus 9. And from here, you can factor this out and find the other two roots, okay? All right, well, let me know if you have any more questions. Some of the example problems in the back of the book or on your assignment might be a little bit more difficult, but that's okay. We can still do them. Just let me know if you have any questions.